Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll solve a problem on outward radial flow reaction turbine. So in our last lecture, we have discussed the theory part of outward radial flow reaction turbine. And in this lecture, we'll discuss one problem on that. So here I have taken a question of in an outward radial flow reaction turbine, the question itself we can identify what kind of question is given. Based on that, we can solve it. The internal and external diameters are 2 meter and 2.7 meter respectively. This is internal diameter and this is external diameter given. The turbine is running with a speed of like 250 rpm and the rate of flow of water through the turbine is 5 meter cube per second. The width of the runner is constant at inlet condition and outlet it is equal to 250 millimeter. That means towards outlet it is increased and here it is constant. The head acting on the turbine is 150 meter and the vane has negligible thickness. The vane is nothing but the blade, okay, have the negligible thickness. And the discharge at the outlet is radial. Outlet condition discharge is radial. Determine the vane angle and the velocity of flow at inlet and outlet. Okay, both conditions we need to find out. The vane angle we need to find out, and along with this we need to find out the velocity of flow. So before going to solve this, first we need to draw the diagram for this actually. So the diagram I have taken from the book, this is the blade. This is the blade we can see, and where the velocity of fluid is entering at one side and leaving at another side. Suppose let's consider at this point the velocity is entering here, and let's consider this is the inlet part. Okay, here it is diameters are given, internal and external diameters are given, and this is our external like outlet part. At the outlet condition, why it is taken like this right angle triangle? Because of VW2 is 0 here. What is VW2? Now when the condition is given, the discharge outlet is radial, then radial in the sense our V2 will be perpendicular to the tangent of the blade. Okay, now here it is, this is the tangent of this blade, this is the tangent of this blade. Now the fluid is entering suppose here with an angle of alpha with respect to the motion of the blade, we can say that is alpha, and this is our relative velocity, so which makes an angle of theta with respect to the blade or movement of blade, we can say. And this is V1, VW1 is a component of V1, VF1 is a vertical component of V1. This is the horizontal component, and this is the outlet triangle. Now we need to find out the solution, like we need to calculate the vane angle and velocity of flow at inlet and outlet condition. So let's write down what are the data given first in this question, that we need to write first. In the solution, first line itself you can write that two diameters are there, one internal and external diameter. So let D1 equal to, this is 2 meter, and D2 external diameter, this is 2.7 meter, and turbine running at speed, that is n equal to, this is we can write this is 250 rpm, and the next is the rate of flow of water through the turbine is like the rate of flow through this turbine, at what rate the fluid is flowing over the turbine, that is given, or we can say this is discharge also can be written in this. So we can write Q, rate of flow, this is 5 meter cube per second. The width of the runner is at the inlet and outlet condition, like we can say width at the inlet and outlet is given. Yeah, width we can write is constant and at inlet condition and outlet. Okay, it is given actually width of the runner is constant at inlet and outlet. That means there is no change of the width at inlet and outlet condition, and that is equal to 250. Okay, that means B1 and B2, okay, width and B1 and B2 inlet and outlet width is equal to 250 mm, and this one also we can write this is 0.25 meter. Next, the head acting on the turbine is 150 meter. So head acting in the turbine is nothing but we can write capital H, this is 150 meter. The vane has negligible thickness and the discharge at outlet condition is radial. So discharge, as I told you, at outlet condition, discharge at outlet, it is given radial, means we need to immediately assume that here VW2 is 0 and we can write VF2 equal to V2. How you got this one? Actually, this diagram initially how used to, it's used to like this. Okay, and this is our VF2, this is our V2, and this is VR2, and this is our V2, and this one is VW2. Okay, this makes an angle of beta and this angle of phi. Now when it is radial condition, then this V2 will be make a perpendicular to the tangential. That means when it is V2 is perpendicular, then what about this value? This value will be 0, and this there will be no angle of this. So here VF2 equal to, we can write V2, and V2 equal to 0 we can write. The same thing was written here. Now here we need to find out vane angles and velocity of flow. To find out that one, we need to first, we'll go one by one steps. I'll find out first tangential velocity. So tangential velocity, this is U1. U1 equal to, we know that pi d1n by 60. Okay, similarly U2 also we can write in this way. So pi into d1, d1 equal to how much? 2, n equal to how much? This is 250, and divided by 60. This can be written like this is 3, so 3, this is 3.114, so we'll get 1 point something will get. Anyway, the value will be 25 into 1 point something, 26 will come. Okay, 25 into pi divided by 3, 26.18 we can write. This is 26.18 meter per second, U1. Similarly, the tangential velocity at outlet condition. These are the basic things, like basic parameters required to calculate the vane angles and velocity of flow. Similarly, here also I can write this is pi into n by 60, and here also again pi into d2 is given 2.7 into n is as usual 250 and divided by 60. This equal to, so how much I got here? This is the same thing, but slightly different, you can say. This is 2.7 given. So here what I got, 26.18. Just I'll do one thing. I'll divide 2, multiply 2.7. No, it will not come like this. Okay, anyway, we'll solve in this way. Like pi into 2.7 into 250 divided by 60. Yeah, same thing came. Yeah, same thing. I just tried in the another method, but anyway, the same value you got. So this is near about 30.34. So you can write this is 30.34. This is Newton per second. Just what I've done, this one divided by this 2 multiplied by 2.7, because our remaining values are same. Yeah, the next is, we know that discharge. So discharge equal to, we know that area A1 and V1. But in this condition, we can write this is like okay, A1 V1 and A2 V2. But here we can write Q equal to, in the place of A1, we know that area of this blade is there. That you can write this is pi d1 V1 area. And what about the velocity here? This is velocity, nothing but flow velocity. This is VF1. Similarly, we can also write like pi d2, and here it is V2 and VF2. We can write in this way. So here what we need to calculate, actually we can calculate the VF1. Suppose let's calculate the VF1, which is nothing but Q by, we can write this is Q by pi d1 V1. So Q value is given in the question already. This is 5 divided by pi into d1 is given 2, and B1 also given, this is 0.25. Now we can calculate this. So this is 5 divided by, we can start the bracket, pi into d1 into 2 into 0.25 bracket close, answer 3.183. So we got here 3.183. This is meter per second, the first one. Similarly, we can calculate the VF2 also. VF2 also same thing. I'll just write here 5 divided by, this is pi into 2.7 into 0.25. So here also we'll get similar ways we can find out. Like what I'll do here, I'll just multiply 2 and I'll just divide 2.7, 2.35. Okay, the same thing I can write here. This is 2.35 meter per second. The previous value what I have done, just I have multiplied this one, again I have divided this one. That's why I dot. Now the next thing we need to find out, yeah. So this is the velocity of flow at inlet and outlet condition. We have calculated this one. So there is no worry about this. That means one answer we got here. Question number 2 we have identified here by this. So these are the two answers for this one. Velocity of flow at inlet condition and outlet condition. Now to find out the theta, the vane angle is nothing but theta. We need to do in this way. Like first we'll use one formula, that is head equation. Actually one equation is there, that is head He minus, this is V2 square by 2G equal to VW1 U1 by 2G by G actually. So this is because of that VW2 is already 0 at this point, and at the radial discharge we know that V2 equal to VF2, so V2 value is known to us. Now this is square actually, so what I can write here, H equal to H is value is given. Actually this formula I told you in the last lecture when we have discussed about the some important parameters required for the reaction turbine. So here H equal to 150 minus 2 point, this is 5 suppose square divided by, this is 2 into G, and this equal to how much, VW1 U1. So VW1, yeah, minus, sorry, VW1 into U1. Into U1 is the value of U1, yeah, 26.18. This is 26.18 divided by, this is 2 into, no, this is only G, V1 by G, that means 9.81, or we can write only G value. So we need to solve this. First we'll solve this one, then we'll go for that side. So what I'll do, take this one here. So 150 minus, I'll start the bracket, this is 2.35 square and divided by 2 into 9.81 bracket close, 122, something we got like this. Okay, first let me yeah, finally we got this one. Anyway, 2.35 square and divided by bracket start 2 into 9.81 bracket close. This is something like 0.281. Okay, this minus 150, let, okay, 149.78. yeah, now we got this value. This is 149 point something 7 I got. This equal to, I can write, this is VW1 and this is again minus rating 26.18 and divided by, this is 9.81 suppose. Then what I can write here directly, VW1 equal to this one, like 149.7 into, this is 9.81 and divided by 26.18. We'll get this value. Yeah, multiply 9.81 divided by 26.18. 56.1. So this value is 56.1 meter per second. I got this value. Now easily we can find out the theta value. So that vane angle theta, we can write this is directly 10 theta equal to, this is VF1. If I take this right angle triangle, then I can write in this way, like VW1 minus U1. So I can write theta equal to, I can write this is 10 inverse VF1 value. How much is VF1? 3.163 or something like that. Okay, 183 divided by VW1. VW1 is 56.1 minus U1 is 26.18, bracket close. So this one will do it here. Yeah, this is something like 3.183 divided by bracket start 56.1 minus 26.18, bracket close, answer. And this is what I told, yeah, 10 inverse. So we got here 6 degree. So the answer is 6 degree. The vane angle is, this is 6 degree. This is our answer, the first answer. Anyway, in this way we can calculate like vane angle and velocity of flow for the turbine when it is given for the outward radial flow turbine. So I hope you understand this problem, how to solve it. Only thing is we need to draw the diagram, and we need to remember some formulas. As I told you, the tangential velocity, this one, and this is the equation, head equation, and these things we can get it from here. Okay, and this one you can get from the diagram also. So I hope you understand this problem. Still, if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you.